Okay, so we've gone through and discussed the concept of solving nonlinear equations, and we know which equations we need to solve for, right? We need to solve for the power balance equations, for the ones that we can. So essentially, what we're going to do in this point is we're going to actually define those bus types, and there's only 3 that we have to define, so that we can know 2 things. The first thing is, what are the 2 equations, or 1 equation or no equations we write? So for example, is it a slack bus? Well, that'll tell us how many equations we can write and how many things we need to solve for as well. If it's the other 2 types of buses, it'll say the same thing. So knowing the type of bus will allow you to actually simplify and actually write equations. And so that's kind of why we have to do this definition. So a slack bus is another bus sometimes called an infinite bus or a reference bus. It could also be called a voltage bus. And the reason being is, at a slack bus, you know the magnitude and the angle of the voltage, okay? You know V and theta. And the reason why is because you have to have a reference point at some location. You have to say, I know a voltage at this location and an angle. You need a starting point, essentially. You can have multiple references if you want, but you at least have to have one, mainly because of this right here. You'll never know all of the power losses in your system. That won't be fully defined for you. So if you have power lost in a line, how do you schedule all your power at a location? Meaning, if I lose 5 megawatts in a line, based on a certain load flow, I can schedule that power. But then I get stuck, which is, what if it's actually 4 megawatts through there? So a slack bus will either provide all the power you need or absorb all the power you need to make sure your system is balanced, right? All the power in the system is being accounted for, essentially. So that's the key thing for a slack bus. It's going to make up all the differences, because you could never figure out what you need to do. You can make a good educated guess, but you could never get all the terms to start off with. Okay? Question?
If I can ask one.
Yes, of course.
I understand what that would look like in software terms, to make things solve. What does that look like in real life?
In real life, the slack bus would essentially be a bus where the generation, if there is generation there, is allowed to vary as much as possible, or there is some load there that is allowed to vary as much as possible to make sure that that magnitude of that voltage is fixed. The angle is going to be whatever it is, but you're going to pick that as 0, and then everything else in the system will be referenced to that point. So it's not really controlling the angle per se. You're just saying that's 0, and everything else is moving. And so that system will basically say, well, I need to pick up the P and the Q as necessary. So a good example in the real world would be a nuclear power plant, right? Nuclear power plant can dump out as much P and Q as necessary. The problem is that nuclear power plants don't like to shift their output all that much or that quickly. So even though it's a really strong bus, it's not a good bus from a perspective of being able to make up the difference. So you'd have to have a nuclear power plant with some additional generation that can swing up and down pretty quickly. In ISO New England territory, I did some digging to find out what the reference buses are, and I don't have access to the PSSE model. So that's proprietary, SIP protected, which is critical infrastructure protected, is essentially what SIP stands for. So I don't know what the reference buses are. That stuff, it's all buried. Somebody knows what it is. I mean, I could ask the right people, but I'm not even sure they could actually tell me what that is. So,
From a studies perspective, it was a fictitious bus that we create to be able to do it. So like,
you created a fictitious bus, but in the real world, they didn't actually have one?
well, I'm just saying, so from a standpoint of what I did with PSSE,
Yes.
you make your own swing bus. That's just this bus sitting there on a system that's not really there.
Okay, well,
To make it solve sometimes.
okay, to make it solve, but the only problem with that is in the real world, you have to have the P and the Q supplied. So, yeah, so if it's a fictitious bus, I mean, the P and the Q need to go somewhere. So you must have some intelligence in terms of a fictitious bus saying, hey, this is pretty close to a lot of generation, so I'll put a fictitious bus here, and then I'll balance things out in that local area, perhaps, is what I'm guessing. But I don't know. I know in the real world, if you were to do like an industrial, like the University of Maine, you would pick the slack bus to be the utility connection, right? Because Bangor Hydro connection or America connection can pick up as much power as necessary. We're always load, right? We don't have enough generation here to do it. So it's always a positive P coming into the system. But the Q, and the P that will go up or down. So usually when you're doing a load flow from a utility perspective, it's not a big deal. From the ISO territory, that's a bit different, and I don't have enough experience to say qualitatively. I could ask actually somebody to present on, we know a bunch of people at RLC who do load flows all the time. They could, if they could, legally, I don't know if they could share that information because of SIP, but I might ask and see if they can do a discussion on that, just kind of a IEEE PES discussion or something, or class 1. So, all right, so we need to define at least one, and you can have multiples, but usually you have one, and that's all we'll focus on in this case. So here's the key thing. If it's a slack bus, you know V and theta. You do not know P and Q, right? Because that's picking up the slack. So remember, you're writing delta P and delta Q equations. These are your F equations to solve for your X variables. I can't write F of X equations, can I? Because I don't know what power balance is. I don't know what the power schedule that bus happens to be. So I can't write power balance equations because I don't know what it's supposed to be. But that's okay because I know what the magnitude and the angle of the voltage are. So if you have a slack bus, you will write no equations because you have to solve for no variables. Okay? That's the first one. The next one is going to be a load bus, which is the most common. Sometimes we denote it PQ. And we denote it PQ because, P and Q are specified. You schedule power at that bus. Okay? It's a load, so you know what the real power is and you know what the imaginary power is. You do not know what V or theta are equal to. So let's do a little, very odd, it just kind of did that automatically. So let's do a table. So we'll specify the bus type. We'll specify the known, the unknown, and then anything else we'll need. So if it's a bus, it's a slack. What do we know at a slack bus? We know the magnitude of V and the angle of theta. We do not know P and Q. So equations to write? Nada, right? Not a single one because you can't write any equations in the case of a slack bus. In the case of a load or a PQ bus, we know the power that's supposed to be at the load bus, both real and reactive. We don't know V nor theta. Okay? So the equations we have to write are delta P and delta Q at that specific location. Let's add one more, which is our variables to solve. None, right? If we can't write any equations, we can't solve for any variables because we have no equations to solve for. So in this case, the variables we're going to solve for are the magnitude of V and the angle theta. Okay? Hopefully this will make a little more sense when we look at the next bus type as to why I added the variables. Let's look at the last bus, which is going to be a generator bus. In a generator bus, we know P and the magnitude of V. We do not know Q or theta. Okay? Those are unknown. The equation that we can write that we're going to use to solve Newton-Raphson is delta P, right? Because we actually know what P is, so we can check if we have a valid result at that location just by simply writing our power balance equation. The variable we're going to solve for is theta at that bus. All right? And those are the three bus types. Slack bus, sometimes this is called a voltage bus, PQ, or PV. Don't get confused at the different types of names of buses, because if I have a generator here and it's operating at 100 megawatts and it's maintaining a 0.9 lagging power factor, what type of a bus is that generator connected to? We've only got three types. What bus is it? What is it? Slack? A gen? A load? Which bus type would it be? Generator?
When you show the power factor, you're showing both P and Q.
I'm showing both P. I can get P and Q from my power triangle here, right?
So that means load.
This is a load. Even if it's connected to a generator, that does not make it a generator bus. All right? Very important to understand. Same thing with this. That's a capacitor. Let's say it's a 10 megavar cap bank. What type of bus is this? Slack bus? Somebody said load. Well, let's go back to the table. To determine the bus type, you have to have the known values. So somebody said it's a slack bus. Do I know the magnitude of the voltage and the angle? Nope. So it's not a slack bus. Let's go to a load bus. Do I know the magnitude of P and Q? Somebody said I have Q, but to have a load bus, I need P and Q. So is it a load bus? A lot of people are saying no, so we'll pass that one and go to a generator bus, which is a PV bus. Do I know the magnitude of voltage and the real power? No? So that's none of the buses? It's got to be one of the three.
I say load.
You say load? Why is it a load?
You have the Q value, and the other two, you have your unknowns are your Q, so I would say that.
So the comment is it's a load because you know Q, but you have to know P. You can't just say, well, I know 1, so it has to be this. I would argue you do know P at this bus. Doesn't P equal 0 in a capacitor? Oh? You knew P. It's a capacitor. How much real power does a capacitor consume or supply? 0. So you did, in fact, know what P was. You just didn't think you did. All right? So this capacitor bank could be a different type of bus if I wanted to maintain 1.0 volt, 4 per unit volts, right? If I want to maintain voltage, this is a switching capacitor bank, right? Like Chester, where you can increase or decrease the reactive power as necessary to maintain the voltage. So if this is maintaining voltage, what type of a bus is this now? PV or generator bus? Because I know P is still 0, and I know the magnitude of the voltage is 1.04. So don't get confused or don't focus in on the names of the buses. Just because you see a capacitor does not necessarily make it a load. Just because you see a generator does not make it a load. Look at what is known, what is specified at that location. Even if you have to dig a little bit, whoops, to get P equals 0, right? Because that wasn't obvious there. But if it's a inductive load bank, resistive load bank, right? I said load bank. You should be able to tell what those are. But there are some cases when you're switching things on to maintain voltage. So if you do that, that hopefully will make things easier. Sometimes you have to switch to different bus types. So if you are overloading a generator, so when you do a load flow, right, you have a P and a V. Well, at some point, you can't ask the generator to put out any more reactive power. You'll burn it up. So you'll actually switch that from a PV bus to a PQ because you've exceeded the capacity of the generator. And that's called type test transferring, essentially. And I think PSSE will give you alarms, but I think it'll try to overdo it, or maybe it'll switch it automatically. I'm not sure in PSSE.
It gives a warning.
It gives you a warning?
It tells you that it's changing the type of
Oh, so it does it automatically, but it warns you.
bus it's gonna be.
Yep, okay. All right, any questions on that? Because it's super, super important to understand the bus types, because if you don't understand the bus types, you will not be able to identify the equations to write and the variables to solve for. But if you know the bus types and you do this little table here like this, you'll actually pull out all your variables and your equations you need to write. You can do it very efficiently. Yes, sir? Yes, sir.
I guess I'm still confused with the capacitor.
Yep.
Just because, so I understand that like power zero doesn't consume any real power.
Correct, power zero.
If you're not given a voltage, does that make it like a load? Or
If you're not told the voltage, right, you need to know what voltage that capacitor bank is trying to maintain. If you're not given that voltage, then it's all on. The capacitor is switched on entirely. If you're given a voltage that you're trying to maintain that, then it's different. And it actually varies because in distribution circuits, there are ones that you can switch on and off depending on the voltage. Many of them are fixed, but there are a few cases when you would have switch, and it does it in big discrete steps. So it would switch it on, but that's not maintaining voltage. That's just doing like a big clunk, switching over. It's only when you have a StatCom or something real fancy like that when you're maintaining that specific voltage. Generators, though, can switch power factor. They can do that very easily. No big deal. All right, questions? That's where we discussed there. That's the type transfer, essentially. Type switching. All right, now we can do no load flow. We have everything we need. We have an algorithm, we know the equations to write, and we know the variables to solve for. So we're going to write those equations. These are two equations here at the bottom. We've already derived those from our Y bus, and it's only a function of the state variables that we're trying to solve for, right? Or we already know the voltages, as well as the elements inside the Y bus, right? K is part of the summation. So anytime you are connected to bus I, right, bus 2, bus 3, whatever, your value of K is going to go from 1 to however many buses you have in your system. So if you're doing PSSE, ISO New England territory, you've got 80,000 is your value of K. So you have your summation contains up to 80,000 elements. It won't. It'll only contain up to 4, or maybe 8 at the most. 8's the most I've ever seen, but that's essentially all you have. So the voltages and the angles here are your values that you're either the state variables, so those are what you're trying to solve for, or you know. And then the G and the B are from your Y matrix. The other element you have to have are your P generated or P demanded. Why do I need these? Because remember, I'm solving for power balance, right? When I take my P injected and I subtract from it my P scheduled, that should equal 0 when I have the right voltages that I'm solving for, correct? So this, when we did our table to figure out what equations we can write, it's because I needed to know what PG and PD are, okay? Otherwise, I can't solve for power balance at that location. I can't do root solving. So these two equations, again, just to highlight, you get this from Y bus, this, and this are your state variables you're solving for, or you know because it's the bus type is specified. And then these two are from the model, essentially. So that's the load that you have, the load or the supply at a particular location.
Are G and B given values?
They're going to be in your Y bus. So you might have to create Y bus, right? Because that's chapter 2. So you can build Y bus, or it'll be given to you.
And then what would that come from Y-bus? Would that just be?
The model of the system. Y-bus will come from the model of the system.
No, I know, but G and B, so we create Y-bus and just work.
Oh, so the question is, where did G and B come from? So remember what Y-bus equals. It's going to have some element in here. We'll call it Y11, Y12. Y11 has a real part, G11, plus or minus an imaginary part, B11. So the G and the B come from there. Remember, you'll note, and I was doing this very specifically, and I talked about this in the last class, you will note that B11 does not contain the J term, does it? I pulled it out separately from there. So your B term should never have the J term in there. You should strip it out. Because if you do that, the Q equations and the power equations now have real and imaginary parts. What we did when we built our P injection equations is we multiplied everything out and then we factored it into the real and imaginary terms. So we've already stripped out the G term, the J terms in advance. You don't have to worry about that. That's been done for you. But do not put those in there. Okay?
They do belong in the Y-bus.
They do belong in the Y-bus matrix, so that way you know which is the real part and which is the imaginary part. But in your power injection equations, you've got to take the J term out of there and just make sure that that's a placeholder to show where the real part and where the imaginary part is. Okay? All right, so we've gone through this part, right? We had that table to give us our knowns and our unknowns. Our power balance equations are our f of x, and our state variables are our knowns or our unknowns, depending on the bus type. Now we just have to guess. And since it's nonlinear, we have to guess fairly close to where we start. Almost always, your magnitude of your voltage will be 1, and your theta will be 0. And you have to do this in per unit. You cannot do this. I don't believe you can in PSSE. I think PSSE does it for you automatically. You cannot do this in real voltages. Anybody know why? How did the homework go, or the lab go last week when you had sines and cosines? What was I telling everybody to convert their calculator mode to get good results? Got to do it in radian mode, right? Why was that? Because if the angle is too large, going from 0 to 360 is a lot different than going from 0 to 2 pi. When you do those partial derivatives, the algorithm doesn't work. How would it be if you have a system voltage at 34.5 kV up to 765 kV? That's a pretty big change, right? A value of up to 20 times. So doing everything in per unit, everything is around 1 at an angle of 1.1 radians, correct? So everything is going to be within 1 plus or minus 10%, or 0.1, so 0.9 to 1.1 for the magnitudes, and the angles are going to be between positive 2 pi and negative 2 pi. Actually, it's going to be between pi over 2 and negative pi over 2, because if your system voltages are greater than plus or minus 90, you've got something else going on there. So you just limit it to that, and then it works really well. Your algorithm works fine. So we do everything in per unit. So here's a case where you have to do the work in per unit. I don't believe PSSE can do it in actual voltages. So once we do our initial guess, how do we know when we're done? We check, does our power balance equal 0? If delta P equals 0 and delta Q equals 0, we're done. If they're not equal to 0, we have to run through the algorithm. Okay? So those are the power balance equations. This is the P injected and the Q injected. This is P scheduled and Q scheduled. If you just are meticulous about if power is going in, it's generated power. It's a P sub G or a Q sub G. If it's power going out, it is demanded power. It is a P sub D and a Q sub D. So just be careful about putting it properly into those parentheses, and it'll work out fine. You'll get the pluses and minuses correct. Okay? So if you go back here, okay, the question is when I do power balance, right, I'm looking for delta P equal to 0. The question is P in equal to a positive number or a negative number, right? You don't know because depending on which way you reference it, it could be positive or negative. Well, the way that we've set this power balance up, this power balance equation, it doesn't matter because we've defined this to be equal to 0. So as long as you have power generated, that's power going into the bus, right? You generate power, you supply it to the system, that's a positive number. If it's demanded power, you're taking power out of the bus, okay? So if you put PG as a number and PD both put them as positive numbers, you don't have to worry about the signs. I've already laid that out for you. Those signs are already taken into account correctly. You just say it's PD or PG, and you're done. All right? Here's another important thing about the algorithm. And this is more, and if you watch the video for the lab, I talk about this kind of important. And it's more of an advanced topic to describe what happens. But you set your your variables up, thetas first, and then magnitudes of your voltages after that. And you put them in order by bus. And the reason you do the number, right, go from 2 to 3 to 4, all on and on and on, you do those that way just for housekeeping purposes, right? You don't put 2 behind 5 because it would just be confusing, right? So you lay those out logically in order. Same thing with the voltages. Now you will note theta 2, this does not need to be theta 3. Whoops, I said 3. This does not need to be theta 3. Do you agree with that? It only is going to be theta 3 if you have to write a power balance equation at that bus to solve for theta 3. So if bus 3 is a slack bus, for example, or if theta 3 is a, well, it wouldn't be, so if it's only a slack bus, you wouldn't have a theta 3. You will note there's no theta 1 or V1 here because I was saying in this case, your bus 1 is probably going to be your slack bus. Doesn't need to be, but it's probably. But you don't have to have theta 3, theta 4, theta 5. It just depends on the bus types you have. Same thing for the magnitudes of the voltages. You don't necessarily have to have numbers for those. Those are just unknown. So this is X unknown, right? These are the ones that you need to update. So these are the unknown values. Your f of x is going to be all your power balance, your real power balance first, and then your reactive power balance secondly. And the reason being is because your theta is determined from your P. Your voltage magnitude is determined from your Q. Do you remember way back when we were looking at transmission lines and I said power flow can almost be exclusively determined looking at bus magnitudes and bus angles, and how I said real power flows from higher magnitude or higher angle to lower angle, and reactive power flows from higher magnitude to lower magnitude? That's actually shown in more detail here. All the voltages are shown from Q.
Can you say that again, real power?
So from our transmission lines, right? If we said our X over R ratio is high enough, if this is V1 at an angle of theta 1 and V2 at an angle of theta 2, I can tell you the direction of power flow. It's just based on if theta 1 is higher than theta 2, then real power flow flows from bus 1 to bus 2. Q is going to flow from V1 to V2 because those have a higher magnitude and a higher theta. So real power flows by the angle. Reactive power flows by the magnitude. Okay? Does that clarify? So again, if you're really comfortable looking at load flow, you can just look at results, and you just look at bus magnitudes and angles, and you can tell, well, that seems really wonky that the voltage difference here is that high, because the reactive power doesn't seem like it should be that high. So if you've got people that have been doing it for a few years, they can just look at quantities and they can make an assumption saying this is right or this is wrong just by looking at magnitudes and angles. Okay? Here's the algorithm. Look familiar? You did it in lab. You did it on the homework, right, with x squared minus 2 starting at x equals minus 1. This is the algorithm. The only difference is this function, and this function are variables. Are matrices, meaning they contain more than one value in there. All right? So that's the algorithm we're going to employ. Here's our Jacobian matrix. So again, we talked about, it's just the partials of all these functions with respect to variables. This is the layout. It's not super duper useful until we look here. So remember how I said right next to your rows, the power balance equation that you're solving for, the f of x, and then right next to the columns, the variables you're solving for? I did that here to provide clarity. So P1, P2, on and on and on, Q1 and QK. And this is not necessarily the bus, this is just the power balance equations you're writing. Also the same thing for the thetas. Those are going to be the state variables you're solving for. And the reason why you do that is because you will partition the matrix, whoops, like that. You'll partition it because it's called sensitivity analysis. Looking at that Jacobian, you can see the partial of P with respect to theta is essentially telling you how sensitive power flows are as you change theta. So if you're an operator at ISO and you're trying to increase real power flow through a line, you can actually look at the sensitivity matrix and say, well, there's a partial of P with respect to theta, let's say 17. If I goose the angle at 17, what kind of sensitivity is going to happen for the power flow at this particular bus? So when you get into more advanced topics or advanced analysis, you look at things called sensitivity analysis, and then you actually make that approach. That's the approach you take to look at that. And if you understand it, it helps you quite a bit. But that's sensitivity analysis. This one I showed you as deltas here. Don't worry about it. Theta or delta can be used interchangeably, and I'll do it in this class quite a bit. And the reason why I talk about delta is because, remember we talked about power flow is based on a torque angle. So sometimes you see people talk about it as a torque angle. Sometimes you see it as a theta. But just pick one that you like and go from there. Let's go back up, and we'll just look at these really quickly. These are all those partial derivative equations. This is if you just wanted to write a script or MATLAB code or want to do your own Python programming to automatically calculate partial derivatives. All the partial derivative stuff has been done. This is just automating the process. So a computer program doesn't do a very good job of doing partial derivatives, but if somebody's done it for you and sort of formalized it with this approach here, you don't need to worry about it. It's done for you. Okay? So all we're saying here is that these are the equations. If you don't know how to do partial derivatives, just let I equal the bus you're looking at, and then let K vary. All right? You have to be careful, though, on a couple cases. You notice here, this is the case when K cannot be equal to I. So that's an additional condition. If you're trying to solve for the partial of PI with respect to theta I, you can use this for every case except for when K equals I. Okay? So essentially, if you're at the same bus, you would skip that term. Okay? Do not include it in your summation. Skip it. Same thing for here. So it's basically looking at the partial derivatives relative to the sensitivity to itself. So the partial of P2 with respect to theta 2, the partial of P2 with respect to V2. You would skip those terms. Same thing with Q. When you take the partial with respect to the variables at its own bus, you would use those values. Okay? And then those power balance equations, the stuff of discussion here is all based on that table. So look at your table. And then you got it. Right? Pausing here for processing. Yes, sir.
Kind of with the lab.
This would be with the lab. Yep, but I got a boatload of examples and using the technology to its fullest. Yes, ma'am.
So, does everyone set it up with theta first and then voltage? Nobody does it the other way?
Everybody sets it up. Everybody that I know and every program that I've seen does theta and magnitude of voltage after that. That's all the techs do that. That's all the approaches in IEEE stuff that I've seen. The thing is, was that what PSSE uses? I don't know, only because all that stuff is proprietary and it's behind the scenes. So if you ask somebody who works there who does the algorithm development, they might tell you. But I would imagine just to be consistent and make it easy, because again, you've got a Jacobian that could be 80,000 by 80,000. So if you sort of come up with your own approach, you could come up with some issues.
It's making the angle a bigger priority than the
Nope, it's not a bigger priority, because you got to invert that Jacobian, right? So when you invert it, it's all being done. So it's not a higher priority, it's all the same. Okay? Let's do an example. Let's do a 2-bus example. Bus 1, bus 2, okay? First thing we'll do is we'll use our table, or at least the table in our brains, because we don't have to go back, because that's a lot of scrolling back and forth. So let's use a table in our brain to figure out our knowns and our unknowns for this system. So what are our knowns and unknowns? Well, I have this information here and this information here. What is this information in the box? Pardon? Well, this tells me P and Q here, right? So I know P and Q at bus 2, so this has to be a load bus, right? So I know P2, Q2, but I don't know the voltage at bus 2, right? So I'm missing V2 and theta 2, right? Let me move load to the other side to give myself a little bit of space. Bus 1. Do I know anything at bus 1? I know the voltage, 1 at an angle of 0. This is 1 at an angle of 0. So I know V1 and theta 1. I don't know P1 or Q1. All right? So now I'm going to focus on, I want to write, or I want to solve for the state variables. So I need to know all magnitudes of voltage and angle. I know V1 and theta 1. Uh-oh, I don't know V2 and theta 2. So what I'm actually solving for V2 and theta 2, right? I need to solve for those. What do I need to solve for? Using my power balance equations at bus 2. Well, thank God I have delta Q2. Whoops. Make those a little nicer. And delta P2. Which is a good thing because I know what delta P2 is and delta Q2. So I need to write delta P2 and delta Q2. Those are the power injection equations I have. This is my f of x. And what that's going to do is solve for theta 2 and V2, which is my x equation. Now I need to solve for my Jacobian, which, remember, this is delta P2, delta Q2, theta 2, and V2. So this is the partial of P2 with respect to theta 2, partial of P2 with respect to V2, partial of Q2 with respect to theta 2, and the partial of Q2 with respect to V2. So I now need to write my partial derivative equations for those terms. So I still need to write these equations here, and I need to do the partial derivatives to solve for here. But I can't quite do that yet because the the power injection equations are reliant on Y-bus parameters, right? So there's my Y-bus. You can take a look on how to build it, right? We just have to invert this. This becomes negative J10, whoops. So this is negative 10J is the Y-bus. That's the only element we have. So if you do your Y-bus build, you should end up with this. Okay? Make sense? Whoops. Gotta be really careful about where you grab. It won't move out. Let me zoom in and do it this way. There we go.
I thought B was the J portion of the,
It is the J person.
and where'd that 10 sign come from?
The 10 sign.
Bus 2 power balance equations.
Here?
Yep.
Because it's BIK times the sine of theta, right?
Oh, so where'd the negative 10 come? Oh, I see.
So let's write that down. Y bus is equal to J minus 10, 10, 10, minus 10. So we have that information there. So now we're going to go ahead and solve for our power balance equation. We know the power scheduled, real power scheduled at bus 2. So in the first case, this is going to be equal to 2. And then K is going to start at 1 and then work its way up to 2 because there's 2 buses, right? So delta P2, and I can move this VI out front here because it doesn't change with K. So I've got V2 because I equals 2. Now I'm going to allow my summation, so K equals 1. So I've got 1, V1, times, there's no G terms in here. So both of these cases, they're gone, right? There's no real parts. So I can drop those terms immediately and just head to the B terms. I'm going to pull BI, which is 2, K, which is 1, so it's 2, 1, so that's that term there. So I've got my 10 times the sine of theta 2 minus theta 1, right? Because I is 2 and K is 1. Here, let's write it out all the way. So let's do it all out and then simplify. So this is going to be equal to V2 times V1 times B21 sine of theta 21 plus V2 B22 sine of theta 22. Then I'm going to pull over my power balance equation. Bus 2, there's power that's demanded from it, right? So if I bring over the negative PD1, that becomes a positive, was it 200 megawatts? So that has to be 2 per unit, right? Because I have to convert that to per unit. So it shows you that if you look in the previous description, it's 200. Well, let's just move up. It's 200 megawatts and 100 megavar with a 100 MVA base. Now, V1, right, is going to be equal to 1. BT1 is 10. This is sine of theta 2. What's theta 1 equal to? It's always 0, right? That doesn't change. So you can drop that out. Plus V2 times B22, which is minus 10. Sine of theta 2 minus theta 2. Isn't sine of theta 2 minus theta 2 always going to be the sine of 0? Subtract something from itself, you always get 0, regardless if it's changing or not. What's the sine of 0 equal to? 0. So that term goes away, doesn't it? And then plus 2. So if I collect my terms, I've got V2, V1, which we said is 1, times 10, sine of theta 2, plus 2, which is that equation there. It shows V1 there, right? But if this case, if V1 is equal to 1, you actually could get rid of the V1 equation as well. Doesn't make a difference. Questions on how to do that? Oh, sorry.
So like,
Thank you.
how are you getting, like, where like B21, like, where are you pulling that from?
B21 comes from here, Y bus. This right here is the Y11 location. That's this element, which is equal to G11 plus JB11.
Yeah, I understand that, but like, how about looking at like GI of K, do you get B2 of 1?
So in my summation, right? So we're solving for delta P2, right? That shows you that I there, this is equal to I. So I is going to be equal to 2. Your K term is a summation. So I've got my V equals V2. Now I have to sum it, and now K starts equal to 1. So I'm going to keep, I've got to have my V1 here because K is equal to 1 on the first pass. Then this becomes B21 on the first pass, right? Using the summation? No? All right. Let me scroll this way a wee bit. If I have a summation, let's say 1 to n of we're going to do that summation. So what happens is, to do this summation, you go 3, you allow k equal 1 first, right? Then you add 4. Once you're done the equation, you increment to the next k value. So 3 times 2 plus 4, plus 3 times 3 plus 4, until you get to plus 3 times n plus 4. So it's just a summation expression. So you're just allowing k to increment as it goes. And why is that important? Because it's impacting these values. Let me erase this here, right? So instead of actually putting in a number in the actual multiplication, you're actually doing it to pick out what theta I and theta k is equal to. So that theta k is being changed as that k value is incremented through the summation. All right? Was this pre-calc? Do you remember when you did summations and products and all that stuff? Has anybody not seen this? Has anybody seen it? Maybe it's a better way to ask it. Where? Calc what? Calc 1. We also covered it in Eet422 when we talk about Fourier series, when we do the infinite series or Taylor series expansion, you would end up with that. So if that's a struggle, we can talk about that more during lab, or you can see me during office hours, we can go through that. Okay? Any more questions on that? Good questions. So I'm not going to go through Q2. You can do that for practice if you'd like. Here's our Q2 equation, our power balance, and our P2. And I've written in terms of variables. Now I've got to start taking the partial derivatives to get my Jacobian. So the first one I need is the partial of P2 with respect to theta 2. Remember, everything in P2 is a constant except theta 2. So if I take the partial of P2 with respect to theta 2, this becomes V2, or 10 V2, times the sine of theta 2 plus 2, right? I just reworked it a little bit. This is the one that is with respect to theta 2. And this is the one with respect to theta 2, right? Just rework the terms. So this becomes 10 V2. What's the derivative of sine with respect to theta 2? It is the positive cosine. What's the partial derivative of a constant with respect to a variable? 0. So 10 V2 cosine theta 2. I encourage you to do it for P2 V2, Q2 theta 2, and Q2 V2. Just be careful. Remember how we have a V2 squared, right? If you just leave it in summation term, that you'll lose out, the fact that there's a V2 multiplied all the way out front. So you would just have a V2 times V2, but it should be 2V squared, or V2 times the value. Let's start cranking out iterations. First guess, 1 at an angle of 0. Plug in 1 for V2 and 0 for theta 2. And you end up with 2 and 1. Are those good numbers or bad numbers? Depends on perspective, but they're supposed to be 0, right? If you get the correct results. Are those 0? No. They're supposed to both be 0 when you're done, or very close to 0. They are not close to 0, so now I'm going to plug them into my Jacobian, and I get my Jacobian form. Now I'm going to update my x value. So this is my x of 0. This is the Jacobian evaluated at those x of 0s. This is that f of x of 0. When your calculator's in radian mode, you're going to update, and you're going to get an angle of negative 0.2 radians, and your voltage is going to drop to 0.9 per unit. Started at 1 at an angle of 0. It is now 0.9 at an angle of minus 0.2 radians. Am I done? I don't know. Let's continue. With negative 0.2 and 0.9, plug those into my f of x equations. Are those good numbers or bad numbers? They're getting closer. It was 2 and 1. Now it's 0.21 and 0.28. That's a lot better than 2 and 1, right? So we're moving in the right direction, but we're still not close enough to have an error equal to 0. So we'll substitute into our Jacobian, 8.82 minus 1.9, etc., etc. Plug it in here, and then we now have updated values. It was minus 0.2 and 0.9. Those values have changed, but they're smaller changes, right? So your change is getting smaller, which is a good thing because you're getting closer and closer to 0. So you plug that in for f of x. Now you're getting pretty close to 0, right? You're at 0.01 for both, or 0.02, 0.01 and 0.02. You can update if you don't think that's close enough. And now, isn't that pretty close to 0 for your f of x? Looks pretty close, right? So your final voltages, or your final voltage at bus 2 is 0.855 at an angle of minus 13.52. So in this system,
How did it change from 0.236 to 13.5?
this is in radians to degrees.
Yeah, that makes sense.
This is 1 at an angle of 0. This is 0.855 at an angle of minus 13.52. Remember how we said real power flows from a higher angle to a lower angle, which is the case, right? We went from whatever power has to be injected at bus 1 because that's the only source of energy, and it's being demanded at bus 2. So we're moving 200 megawatts there. So we change 13 degrees. And the same thing for the magnitude. We have 100 megavars demanded at bus 2. So all the reactive power is going in at bus 1. So its magnitude should be higher than at bus 2, which it is. Questions on that?
So Q's going back to the generator.
No, there's a slack bus. No, it's not going back to the generator because the magnitude at bus 1 is higher than the magnitude at bus 2. So the Q is being demanded from bus 2. It's going out of bus 2 to the load. Okay? Questions? Any questions? Here's using a software that the author uses called Power World. So this is the actual result of doing Power World with a 2-bus system, and this is what you would get. You will notice, you can check it yourself. Why aren't these two equal to each other? On this side, it's a good thing, right? Because I have negative 200 being injected, that means it's going out. Negative 100, that's correct, right? Because that's what the load is at that bus. But why isn't this the same as this? Yeah, because a line consumes reactive power, right? It's a big inductor. So you have I squared X that are consumed in the line. So this line consumes 68.3 megavar. So the power injected at bus 1 has to include not only the real part, which is 200 megawatts, and since there's no resistance in the line, there's no loss in the line, real power loss in the line, but there is reactive loss in the line because of the inductor. So that's why you see at the slack bus, you've got 200 and 168.3 megavars, but the load is only the 200 and 100. There's no losses there. Okay? Feel good? Here's the MATLAB script. You like to see it in MATLAB. Is this legible, or should I zoom in a wee bit? Exactly the same equations, but I tried to be a little bit sexier. I actually called it dpt2 and dq2, right? To get the delta powers. Then I've got my Jacobians specified there. I did my JX, and this term here is what's called left divide. That's just another way, a fancier way. MATLAB, there's a bunch of different ways you can invert a matrix, and depending on who you ask, the left divide is more precise. I don't know. I just tried a bunch of different ones. I get the same results. So you can raise it to the -1. You can invert it. It's all the same, at least for what we're doing here. Okay? Then I actually calculated the P and the Q at bus 1 and bus 2, because there should be nothing up my sleeves, right? All that work that we just did, if there's any fancy, trickery that's going on, you can call me out on it. So here's the results of the first iteration that match our results. Same thing for Jacobian and same thing as the angle. Just finished my first iteration, now moving on to the second one. Here's dpt2 and dq2. I updated my values. I continue on. Now I have a new value, which is getting closer and closer. Again, that match. Now I got that really small value, dp2 and dq close to 0. But I'll run it one more time, and I'll stop it at this value. So this is my angle. That's my magnitude. Then those calculations that I did, right, way back here, the power injected at bus 1 and bus 1 for real and imaginary should match, right, what's on the screen. So I said 200 megawatts or 2 per unit power should be injected at bus 1. Looks pretty good there, right? There's no line losses, real power losses, so that's good. I do the same thing for Q, 1 0.63 or 683 per unit reactive power, when I multiply it by 100 MVA, is 168.3, which matches the slide. And then the power calculated at bus 2 is 200 megawatts and 100 megavar that's delivered. So this is all done with MATLAB script. And if you choose to, you can actually type this in and check it out. Pardon?
Thank you.
Oh, you're welcome.
I love free MATLAB.
You don't like MATLAB?
I love free MATLAB scripts.
Oh, okay.
Somebody else has already done.
It's just a simple code, but the thing is these files get pretty ornery really quickly. So it's nice to see how they get implemented. But more along the lines, sometimes when you use software and you just say, here's the software, here's the results, yada, 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 you can set yourself up for tricking yourself that you've got the right answers when in fact you are wrong. So if I just do it in MATLAB, you can say, hey, wait a minute, you got the wrong results. But if I show you this in MATLAB, and this is just a publish file, I just had it as a PDF, so I just ran MATLAB this morning as a publish, and so these are the results it spits out. And you can say, well, you still could have fudge factored numbers in there, which technically, yes, I could have, but you can actually run the script file like this, and you should get the same results as long as you enter it in correctly. Okay? I will pause because you need to think. Are you impressed or burnt out? I'm not sure which.
Great job pulling it all together, Paul.
Wrapping a big bow around it. Tying all those things. Again, this is a pretty tough material because I have to spend so much time showing you how to do the math algorithm to implement it. Then we got to write the equations to solve for it. Then you need some knowledge of what equations you need to write. And then the actual implementation of all that together gets to be complicated. So it's tough. But if you understand this and you sort of understand the concepts of load flow, it really gives you a big leg up on how the system actually functions and operates. Because if you design a substation for company ABC Engineering, right, because everybody has a 3-letter acronym in Maine, it seems like. So if you're ABC Engineering, the idea is that, well, okay, what am I doing here? What is a substation doing? Well, ultimately, it's serving customer load, correct? And how you get into the specifics of the design of the substation aren't relevant on the load flow, but why is that substation located there? And why is the percent Z of the transformer what it is? And why did they put a cap bank on that system? And et cetera, et cetera, et cetera. So you're understanding the operation of the system so that you can have a better sense of, all right, now I kind of get an appreciation of why a substation is needed and what's happening at the upper level. It's not just, okay, let's go dig up the ground and put a ground grid and then put some crushed rock and then put a fence and put some foundations. But you'll get a better appreciation of how the grid's operating. Do you like seeing the script files or do I not bother?
Looks a lot nicer.
Nicer than the slides? I thought the slides looked pretty cool, but maybe not. The nice thing about this is it just shows you how to implement it in a calculator, right? I mean, what I'm doing here in MATLAB is no different what you do on your calculator. You would enter in this equation here in your calculator with the variables shown. And I think in your TI, you can actually define variables as being equal to stuff and process it. So all of that stuff that's done in your while loop, except for the iteration, you would just do that manually if you want to do your calculator. And then you can check your work. So if you're feeling a little bit, hey, I want to check to see if I can run through this with my calculator, you have all the iterations to walk through. So hopefully it makes it simpler. Any questions? You can also do it with a bad voltage. If I start at not 1 at an angle of 0, but 0.25 at an angle of 0, are your customers going to be happy that the voltage is at 25% of what it should be? Probably not. But from the load flow Newton-Raphson algorithm's perspective, it'll work perfectly fine. So I didn't bother doing the MATLAB script file for that. You can just see the results. But you can run through this whole process. And here's your final solution. Is this a good solution? Well, our voltage is pretty close to 0.25. And we do deliver 200 megawatts at 100 megavars, don't we? Look how much reactive power is dumped into that line and is consumed by the line. 732 megavar of reactive power has been consumed in that line. Which makes sense because that's how much voltage it needs to drop a ton of voltage, right? If you're at 1 at an angle of 0. So the way that you do that is you have massive amounts of current flowing through this system, and you get a huge I squared X to give you the voltage drop you want. It does meet the criteria, but in the real world it wouldn't happen because if you ran the line with that much power loss, you'd say bye-bye to the line, right? Wouldn't exist very long. Yeah, because it's all I squared, so it's the magnitude of I. So your P and your Q determine the magnitude of the current. Your Q went from 163 or 168 to 832, right? So you're almost 550 megavar more power. Your current has more than doubled. So can the line handle that? Probably not. So that's why starting at the right value is important. Okay? Do you want to try to cram in the PV bus, or do you want to just watch the lab discussion and do it here? Who wants to try to cram it in? I got 8 minutes. I need to know from you how burnt out you are, or I can jam it in. All right, well then you're responsible for what are you going to do today? You're going to watch the video for the lab. Make sure you put the time in. I put a lot of effort. I think I put 5 hours in on Sunday to hopefully have a quality lab experience. So I put the lab there. I actually showed you how to get all the equations. So how do you define the unknowns and the knowns, the equations, also what partial derivatives you need to take, and sort of walking through. And I included the script file for you to go ahead and check and see. So my hope is that this is a learning opportunity and not a copy opportunity, but I'll leave that up to you. All right, have a great day. Oh, question.
The lab we did last week, are you expecting a lab write-up for that? Or?
Yes. You got to explain it to yourself, yeah? So that's the other thing too, is if you do not want to come to lab, again, I'm not, if you understand it, it's your call. You do not have to come to tomorrow's lab. So you can turn in lab number 4 on Thursday.